Sorry, what was that?
Oh yeah, you can please start now. Yeah.
Okay, great. Hello, everyone. I'm Andrew Beaulieu. It's a great pleasure to be part of this workshop today. I'm part of the Large Behavior Models division at TRI. I lead our platform team, which encompasses a lot of our robot, or encompasses all of our robot hardware and a lot of our core robotic systems. So I wanted to present maybe a slightly different talk that covers a breadth of what we're working on towards platform research up through integration as we research large behavior models, and I'll get into that a little bit. But this will cover research and development within the division and provide some lessons learned, especially through policy and hardware interaction and iteration, and share a little bit about where we're headed in the future. Uh, oops, sorry, there it is. So at a high level, our mission of the LBM division is to pursue fundamental, open, use-inspired research on the new science of learning language-conditioned visual motor policies at scale. So this is just our high level where we're headed. Um, and to sort of define what an LBM means, or to clarify, just so that we're on the same page here, we've seen very public breakthroughs of large language models and visual conditioned language models. LBMs are a multitask language conditioned visual motor policy. So at a high level, we're looking at including robot data and images, consuming those perhaps with a language prompt and producing robot actions. And this talk won't be focused much on the actual details or implementation of the policies, but more of the interaction towards hardware control and where it sort of interfaces with a lot of classical robotics. So to make these data sets a reality, to actually train these models, we've realized that the platforms have really become vital. And that's the hardware and control and how you actually perform with these. So teleoperation, if you're going to do that, or any sort of mechanism to control or plan with them. And TRI has put a lot of effort into stabilizing our hardware pipeline and then scaling somewhat to create more high quality data to train these policies. And I'll explain more about what we've done and where we're headed there also. And then the operation of these policies on real hardware has also been crucial to studying and evaluating the policies themselves. So from there, I actually want to take a step back to present a little bit of prior work on a project called Punyo. And some people might have heard of this a year or two ago when we were working on this project more steadily. But Punyo is our robot's name, but also a design philosophy for what a home robot should be. Its name describes something soft, cute, and resilient. So the research we did for Punyo really was TRI's foray into compliance and sensing towards whole body manipulation. We took the approach of a rigid skeletal structure with classical, like a hard arm underneath soft sensing. So soft compliance and sensing to actually sense the world, but also comply and make sort of rich contact. And then we use this to explore whole body grasps and interactions. So during this time, we basically diffusion policy research was heating up within TRI and within across the robotics space. So we started actually training models with these with Punyo data. So we found success in training policies with tactile signals from the arms, and we were able to generate these whole body grasps and behaviors. So this example here actually includes a controller we developed also that has compliance, basically in the like joint level compliance, so that we're actually able to interact with it during the rollout of the autonomous task. So we quickly found that we needed additional degrees of freedom. So this was one of the lessons learned from this project. Particularly this robot, we ended up adding sort of at the base frame of where the robot arms meet, we ended up adding a hip pitch joint to open up the workspace. We needed to reach further and then to make really robust grasps of large objects. A tilt backwards actually really helped in creating a caging grasp. So this project really allowed us to explore a really interesting space and start feeding new robot signals into diffusion policies. So going forward, about a year ago, we created this LBM division, which I introduced initially. And this allowed us to bring a lot of lessons learned from some prior research in diffusion policy and some of the things we learned from Punyo as well. So we established a focus on sort of enabling the research of these models. And one of the forefront barriers was high quality data, especially on an embodiment that you readily had access to, and access to using and studying and improving along the way. So the next phase of this for LVM was to build out these stations. So these ones, I think we've shown quite a bit in other talks towards especially policy research and things. But the stations themselves are bimanual, so two-armed, Franca Research 3 arms. We still affectionately call them pandas, which is their prior generation name. So they'll forever be pandas for us, I think. But we settled on basically a two-scene camera plus two wrist camera per arm approach. It kept things relatively simple and it sort of fit a minimal set of inputs for the vision systems to actually start researching these policies and gather reliable, high-quality data with. And we developed some good teleop systems and actually worked on optimizing the control so that we had good reactive control with these. We used the Space Mouse and Oculus controllers. So we did all this. We sort of established this as an MVP of like what we thought would be good enough to actually collect a good amount of data that would actually be very rich and useful. And then, so we scaled these to, I think it was like 8 or 10 stations. I probably should have the count somewhere to actually run data collection against. So one of the key lessons, which maybe it's obvious, but I think it's worth talking about a little bit, is that the hardware, like the hardware systems and embodiments that you create actually very much shape the data you can collect. And downstream of that is what you can train for policies and what you can do with these. So the platform really does define the nature and quality of the robot demonstrations. Um, where sensors are placed are actually also something that ended up being very interesting and limiting if not done right. So how they're configured directly influences where the robot sees and senses. And places like or coverage and inclusion and alignment are places where you could really have pitfalls for what the policy eventually learns. The robot's embodiment and workspace actually matter, of course. The kinematic reachability of the static stations end up placing a lot of constraints on what you can do with the robot. Um, so additionally, constraints are introduced by hardware that you add. So as we're adding cameras and other things to this or wire assemblies or anything like that, the occlusions that are created or the collision boundaries that are created really start to impact what you're able to do and how you're able to sense. So these were things that we learned some of them the hard way through ending up with occlusions in the wrong place or ending up with lenses that were getting bumped or something like this. Um, Additionally, with this LBM 1.0 hardware, we could quickly see the limits of the static arms. So not being able to move around really was one of the main ones, but also if we just had an additional hip like we did with Punyo, or if the cameras could actually move their pose, which they were just static scene cameras at this time, it could have really helped. So all that being said, there's a lot of nice to haves, but sometimes simplicity wins, I guess until it doesn't. But our static arms gave us this stability and control in the demonstration data that was being collected and the evaluation of the policies also. So that was sort of a really great advantage to this that I think probably ended up really paying off well for the data that we collected and the like ability that we have to actually evaluate the policies. So it was a really nice advantage. And one of the places to really look towards for the simplicity versus complexity is the gripper itself. So the station actually, the systems we were using these parallel jog grippers, which are obviously very common. But they ended up being very reliable and honestly quite surprisingly performant, especially if you have a nice finger design. We've worked on these fingers for a while, and I think a lot of other people have adopted some versions of these also. But adding compliance where it's where it helps a lot in very specific places in the finger, plus the friction really goes a long way. Additional to this, which was a bit of a surprise, was that our robot operators ended up being remarkably creative around task strategies, especially with limitations that were introduced by hardware. So they learned teleoperation methods that would force the robot into different configurations. So if it's like a different arm configuration to get around obstacles in the scene, or even just to have a certain approach angle if they're going to grab a certain object, especially if you imagine reaching into a shelf, being able to get, if you're only doing end effector control, being able to get the other degrees of freedom out of the way is not one-to-one with the teleop methods that we had at that time. So those are things that sort of won towards the simplicity side. But of course, there's a limit to the simplicity. So broader, more rich robot tasks will certainly require more dexterity. Oops. So the result was lots of LBM data. So this, oops. Yeah, this mosaic is a bunch of demonstration examples um, from the data collection. I don't need to go through all this, but we ended up with 500 skills, 500 hours, and then a bunch of mix of sim and real towards the policy. So I wanted to sort of just show the result. It's more of a brag for them from the policy standpoint, but the platform sort of served its purpose, gathered a bunch of data, and then we ended up having these really surprising success cases. This is a long horizon scale. It's obviously sped up. Um, But this was an Apple coring and cutting task. It's end-to-end run autonomously. So it grabs the knife, takes off the sheath, cuts it up, or cores it first, and then cuts it up, and then wipes the knife, and it's done. And we actually got surprisingly good success rates out of this. We have lots of metrics that we'll release very soon, actually, in a paper for our LBM 1.0 paper that'll be coming out in a couple of weeks, we hope. Um, but we actually had quite a bit of good success for end-to-end runs there. And the things that end up failing were actually surprisingly, interestingly, kind of logical in how they do fail, which is kind of nice. Meaning they would do natural things like a human might do if they get confused or something like that. So where we're headed for LBM 2.0. So our team has been working hard across hardware and software integration, sensor bring up, controls, teleoperation, and data tooling for our next platform. The strategy is somewhat similar to the previous station, where we leverage these off-the-shelf robot systems for scale and reliability, and then add custom hardware, sensors, compute, especially leaning towards things that we already have like established success with in LBM 1.0. And we'll build great teleop interfaces to allow the operators to pilot the systems effectively. So our progression looks, I guess, a bit like this, but maybe with less emojis. This is a sneak peek on the right of what is our new prototype system, but it's based on Rainbow Robotics RBY1. So toward that, we have some hypotheses, which is some of the routes we've taken to customizing this hardware already. I guess to start, one key enabler we've had was actually establishing a really good relationship with a vendor that you can work with for robotic hardware if you're not going to sort of spin your own actuation chain end to end yourself. So for us, that has been Rainbow Robotics. We had some people over there that we were friendly with, and we were able to actually work with them on producing some variants of the robot that will allow us to do some different things based on some things learned or some hypotheses we have. So the first one is actually that holonomic drive just might simplify in a really great way to start the learning interface for mobility or locomotion. And not just omnidirectionality, but the actual holonomic drive. So not having the non-holonomic constraint should actually hopefully help, at least in the start of the policy interface. And basically not wrapping another planning layer into what the policy has to learn. And then the other piece that was sort of a pointed thing that we were looking towards is a neck to actually swing the sensory suite around. So we have multiple cameras up on a neck, and we wanted to create a multiple DOF pivot or actuation chain so that you can actually drive your cameras to where they want to be or to the view you want to have. And this is for a few reasons. But one of them, which is sometimes not obvious, is actually for steering attention. So being able to put the camera view where you want them is good for the teleoperator if you're looking through those sensors, but for the policy to actually give it attention cues. And obviously, the other great thing is you actually spend more pixels on what you actually want to see, what the wants to see, but also or what the robot operator wants to see, but also the policy probably wants to see. This is just a quick, bigger view of our robot, what a robot station will look like as we're prototyping it, and we're starting some data collection. So another key area here was basically teleoperation or the interface. So the hardware and human interfaces, those definitely matter. So a good teleop produces better data and we think better policies, hopefully. So far that's been true. We've been trying to prove basically the performance of teleop increase with policy. One of the methods we're using is VR technologies. So the top thing is a space mouse. I'm sure some folks are aware of these mice for CAD or for robot operation as we know them. But we usually use those for end effector control or something like that. But things are very quickly changing towards VR-based technologies that are cheap. They offer great methods for augmenting operation because they provide a lot of good control inputs. Um, but a couple of the things we've learned is sort of optimizing for operator comfort and design are actually really important, especially towards operator fatigue, which is it's a real issue and it happens quicker than you might think in trying to operate these robots for even minutes to, tens of minutes. Um, so towards that, enhancements like overlays and screen feedback should allow for better piloting, and we've seen that already. Let's, oops. So here's, it's still a work in progress, but we're working on some of the control systems for this. Um, the iteration of and research of teleoperation has been so tightly coupled with our control choices and how we implement controllers. So this is one of the examples that we were working on. Right now, her hands are not being tracked. There's a lockout mechanism, basically just one of the buttons she's not using to control this robot. So this was about basically steering the robot's attention with the head and being able to keep the end effector static, and then you'll see actually the full end effector control plus head. Hopefully in a moment. Oh, okay, there we go. And I must say, trying to judge the control of a robot through Zoom is probably one of the worst ways to do it. So I apologize for that. Um, let's and just as another sort of sneak peek to what we're working towards with the future, there's a lot of learnings we gathered from Punio towards the compliance and sensing. We don't have much to share yet on that, but it's something we're very keen on researching further and implementing onto our new systems. So building out a lot of this compliance structure along the arms for whole body grasps and chest and other places on the robot. The right sort of alludes to that with the arm, but really getting towards how can we add this softness for something that can interact in a human environment in a sort of more pleasant way, and then also be pretty performant in how it grasps objects, specifically whole body things or something like that. But there'll be more on that in the future. Here's another teaser video. I mentioned we made the choice of going with a wheeled base, and that was largely for simplicity's sake. But we also have a collaboration with Boston Dynamics. This is their eAtlas, and we're working on them with training policies. So we're actively partnering on, gathering data for their humanoid systems, and then training and co-training with mixed variants of data. So we might mix this with data that we have on our platform and then see sort of research how we can do the cross-embodiment transfer or just create a large model that you fine-tune with specific embodiments later. So this specifically, I wanted to call out as sort of interest because on the platform side also because we chose not to go into legged locomotion. This is a pretty awesome teleop that they were working on that allows them to control whole body with their teleop system. So they're working on some of this to complement some of the stuff we're working on too. So it's a pretty cool collaboration, and there'll be more to come publicly on some of the research and results we've had from that. And I wanted to call out a few other places we're learning a ton from. So simulation has just been a key player in a lot of our work. I mentioned some of our data was taken from simulation, and we basically mock our platforms up in simulation. We don't right now do much iteration towards hardware in the simulation, but it's been vital in actually getting to performant policies. I mentioned the TRI Boston Dynamics collaboration, and then obviously the UMI or UMI interface, Universal Manipulation Interface, has a pretty cool place in data collection where it's a nice portable interface. We think that has some pretty cool promise and might actually supplement a lot of a lot of the task data that we might need. And then obviously any partners and researchers, like anyone who attends RSS and workshops like these. We're learning a ton from the community right now and hopefully providing a little bit back for other people to work with. So I think I ended a little early.
Thank you Andrew, for the wonderful talk. We're now open for questions. Yes.
Okay. Hi, Andrew. A question. So you mentioned good teleop leads to good data, then further it leads to like a better performance, better policy. Do you guys have any metric on what good data should look like in like robotic manipulation? Also, like you guys have like data collected in simulation in like different teleoperation devices like UMI, like Space Mouse or haptic arm. How do you compare like the data quality of those data collected from different methods?
Yeah, I'm not sure we actually have a metric to decide what the quality of a demonstration actually is. And I guess that's a great question and a great place to look for because what do we actually mean by high quality data here? In the vague sense, it's that it has enough rich contextual information where there's a lot of image disparity of what you're looking at or basically enough features. We're sort of guessing at what the policy really wants to consume in this case, and we're probably lumping a lot more into how well the policy performs once you feed that data in. So I guess the metric is sort of evaluation criteria on the output of the policy, which is a longer cycle, but maybe at the end that's actually what matters. We haven't seen much disparity in teleop interfaces as much, but that's with the exception that the LBM 1.0 data was all static systems. I believe if we were to have variance in tasks with the new systems where it's like locomotion and head tracking is very different, I think there'd be very different results of what's learned. And that's because the control mechanisms are very different when you get to locomotion, how you move the wheeled base around and how you move the neck around. There's a lot of control choices there. And the mapping from the teleop to the control. You can see trajectory differences for sure between free-floating Oculus controllers versus a Space Mouse. There's definitely artifacts there, but we haven't had trouble mixing the data, and we haven't necessarily, I don't think we've ablated which controller might have a better success.
Okay. So is your large behavior model aware of like which control policy you are deploying on the robot?
At some level it is. I don't know how far into the policy it actually gets fed. Most likely it doesn't actually use that information. It's a piece of information we log at the platform layer. But we haven't to my knowledge, I don't think we've trained policies that have any sort of divergence across basically teleop input mechanism.
Thank you.
Mhm.
Do I forgot that?
Yeah, you have it.
Andrew, thanks for the talk.
Yeah.
I'm interested in knowing a little bit more about your tactile sensing, specifically when it comes to the new policies that you're training. Are you closing the loop with a teleoperator at all, or is it just for training your new policy?
Tactile sensing in the newer systems is a bit of an empty space, unfortunately. Meaning we haven't fully fleshed out where we're headed with new grippers yet. Towards the whole body tactile sensing, so larger scale, we will definitely be working on that. Towards the dexterity end of like traditional tactile sensing at the end effector, it's basically an open search space right now for us. It seems difficult for us to build our own hand and compete with all the hand options there. So hopefully we get some of that from a really awesome hand that comes out. Unfortunately, it will be at a cost. They're quite expensive now, but there's a lot out there for hands, and we just need to work with them to see what's going to actually be feasible for us in the future. So right now, the direct answer is there's no tactile input into the policies for the LBM versions. The only tactile data we've shoved in to diffusion policy was the Punyo version. But that seemed to work okay. It had signs of life where it would grasp something until a certain pressure value or something like this, when we're talking about like air pressures on the arms or something like that. So there were already signs of life, and we already sort of know how to do it. It's just a matter of actually plumbing that through. On the teleop end, right now with the immersive displays, we're trying to offer feedback to the teleoperator as like additional features. So there's certain feedback mechanisms we'd like to explore, like maybe plumbing through joint torques when they get towards a maximum or something like this. And specifically, it's not intuitive to operators, obviously, that there's a lot of force on a joint when they're focusing on, especially when they're focusing in a different place. So if their arm is up against something, it's very unclear until you hit a fault or something like that. So visual displays or something like that might work. We've explored haptics in the past, and we have some research and videos on that, and it's been promising. It's just the right device isn't really out there for us that we've seen so far. In the VR, freeform VR, where you're wearing a headset, you don't have other constraints on your person, actually seem to be a little bit more comfortable and more functional right now.
Man.
Does that answer?
Yes. Great answer. Appreciate it.
Thank you, Andrew, for the